So our first session will be on attribute-based encryption and functional encryption. And there will be 3 talks in this session. Our first 2 talks will be virtual talks. So without further ado, the first talk will be multi-input quadratic functional encryption, stronger security and broader functionality by Shweta Agrawal, Rishabh Goyal, and Junichi Tomida. And Junichi will be giving the talk over Zoom.
Okay, thank you for introduction. And this is joint work with Shweta Agrawal and Rishabh Goyal. So let's start with functional encryption. And functional encryption is an advanced cryptographic notion, and typically in the FE system, an authority generates a public key and master secret key. And using the master secret key, the authority can generate a secret key for some function f, and a user can publicly encrypt a message, and the decryptor will take a ciphertext and secret key, and decryption reveals only f of x and nothing else about x. And multi-input functional encryption is a generalization of functional encryption, and which can handle multiple input functions. And in this talk, I will use 2 variants of MIFE. And first is a secret key MIFE, and the second is a standard MIFE. And basically, secret key MIFE is a weaker primitive than standard MIFE. So first, I will explain secret key MIFE. And setup and key generation algorithm are the same as single input FE, but in this case, this function f can be multiple input functions, and encryption algorithm takes the master secret key and the index of slot, and it outputs the ciphertext for the corresponding slot. And the decryptor takes the ciphertext for slot 1 to slot n, and the secret key, and decryption reveals only f of x1 to xn, and nothing else about x1 to xn. But the problem of the SK-MIFE model is that the security of the system is broken if one of the encryptors is corrupted because it leaks the master secret key, and the adversary can completely decrypt all ciphertext. So to avoid the problem, we can define the standard multi-input functional encryption, and in which encryptor uses distinct encryption keys for each slot. So in this setting, we can consider a meaningful confidentiality for ciphertexts in the uncorrupted slots, even if the adversary can corrupt some slots of some encryptors. So okay, so this model can capture the more realistic threat, and it is more desirable and challenging to achieve an MIFE scheme than achieving the secret key MIFE scheme. And so let us recall the previous works for multi-input functional encryption. The early works focus on the function class of general functions such as or circuits or Turing machines. And they consider a stronger MIFE model, but the disadvantage of these works is they rely on obfuscation. So this is a non-standard strong assumption. And the first MIFE scheme based on standard assumptions is constructed for a simple inner product functionality, and in the weaker secret key MIFE model. Later, these works improved, and they obtained more stronger a stronger MIFE model, and they also achieve a labeling functionality. And the labeling functionality allows users to attach a label to each ciphertext, and decryption is possible only when all labels are the same for all throats. And standard MIFE with the labeling functionality is also known as multi-client functional encryption, or MCFE for short. And last year, we proposed a secret key MIFE for stronger functionality, that is quadratic functions from MDDH assumption in the pairing groups. And we call this scheme AGT scheme later on. So natural question is whether we can obtain the quadratic multi-client functional encryption for quadratic functions from the same assumption. But we tried to achieve this, but we couldn't. But instead, in this work, we achieve this functionality or security separately. So our first contribution is the standard stronger MIFE scheme for quadratic functions. And the second, our contribution is construction for SKMIFE for quadratic functions, plus labeling like multi-client functional encryption. But achieving these properties simultaneously is still open problem. So due to the time constraint, I will focus on the first contribution in this talk. So high-level overview of how to achieve the standard MIFE for quadratic function is as follows. So we've observed that SKMIFE with a special homomorphic property P can be generically converted to the standard MIFE for the same class. And that we found that the AGT SKMIFE scheme does not satisfy the property P. So we modify the AGT scheme to satisfy P and apply the conversion to the modified scheme. Then it results in the standard MIFE scheme for quadratic functions. So what is the property P for SKMIFE? So it states that for all slot I, there exists elementary messages E1 to E sub D and an efficient algorithm Encryption, such that for all messages, the following two distributions are the equivalent, statistically close. And this indistinguishability says that the output of encryption algorithm can be simulated by the ciphertext for elementary messages. So if we have the SKMIFE scheme with the property P, then we can convert it to the standard MIFE scheme by setting this Encryption as an encryption algorithm, and the set of ciphertexts of elementary messages as encryption key in the resulting MIFE scheme. And intuitively, the ciphertext can be revealed to the adversary even in the SKMIFE setting. So if the adversary corrupts encryption key in the MIFE model, still so it does not harm the security of SKMIFE. So we can reduce the security of MIFE, the resulting MIFE scheme to the underlying secret key MIFE scheme. And so then I will explain how to achieve the property P in the AGT scheme. And if AGT scheme satisfies the following homomorphism, and this denotes the ciphertext for vector x1. And then we can set elementary messages to be the vectors of the canonical basis, and Encryption works as just adding the ciphertext for elementary messages in a coordinate-wise manner. But in the AGT scheme, this is not the case. To see this, to see why, I will explain the structure of AGT scheme. And a ciphertext for vector xi of the AGT scheme can be written like this. And this bracket notation denotes the element-wise exponentiation to some group in the pairing groups. And here, MI is the common matrix for all ciphertext in slot I, but VI, while VI consists of the following elements, one or an entry of xi, or a random element in ZP, or an element of the tuple of this form. And we do not go into the detail, but we found that the element in item 4 is problematic in that for homomorphic computation, but we show that the element of item 4 can be removed from the AGT scheme. So if we can remove them, then the rest of elements are amenable to the homomorphism like this. So it turns out that the ciphertext for x1 plus x2 minus 0 is equal to ciphertext for x1 plus x2. And subtracting the ciphertext for 0 is important because otherwise the elements in item 1 becomes 2. So to maintain the elements in item 1 to be 1, we need to subtract this term. And at this point, it seems that we can achieve the homomorphic property P, but this is not the case. So this is not true because the random element in item 3 is not freshly random after the homomorphic computation because they depend on the elements in item 3 in these ciphertext. So to randomize the item elements in item 3 after the homomorphic computation, we need to add in this term. And the point is that the elements for item 1 and item 2 in this red part is are 0. But the random so elements in random 3 is still some random elements in this ciphertext. So by multiplying fresh random element Rj, then we can randomize the only elements for item 3. So adding this term to the homomorphic computed ciphertext, we can randomize the elements in item 3. Then at this point, we can achieve the homomorphic property P. So let us summarize our talk. So in this work, we obtain a standard MIFE for quadratic functions and the secret key MIFE for quadratic functions with leveling functionality, but we couldn't achieve them simultaneously. So our open question is whether we can obtain MIFE for quadratic functions with the leveling functionality from a standard assumption. So this is also known as a multi-client functional encryption for quadratic functions. So it is interesting open problem whether we can achieve this from standard assumptions. That's it. Thank you very much.
So we have time for one question. Anyone? So can you comment briefly on why your techniques does not suffice to get multi-input FE with labeling?
So I think achieving the labeling functionality, we use a pseudo-random function, and the pseudo-random function works in the secret key setting. But if adversary can corrupt some slots, then the PRF key is revealed, and some security issue comes in that setting.
Okay, cool. Thanks. Are there any other questions? If not, then let's thank the speaker again.
Thank you very much.
So I think our next talk is also remote. So do we need to switch the Zoom? Ah. Okay, so our next talk in this session will be on bounded functional encryption for Turing machines, adaptive security from general assumptions. This is a work by Shweta Agrawal, Fuyuki Kitagawa, Anuja Modi, Ryo Nishimaki, Yoshoda Yamada, and Takashi Yamakawa. And Anuja will be giving the talk.
Thank you for the introduction. So let us start by defining what ciphertext policy functional encryption is. The setup algorithm takes the security parameter, the size of the policy F, and the collusion bound Q as the input and outputs the master public key, master secret key. Here Q is the bounded polynomial collusion bound. The encrypt algorithm takes the master public key and the policy F as input and output ciphertext. The keygen algorithm takes master secret key and M as the input and outputs the secret key, and the decrypt on input the secret key and ciphertext outputs F of M. The correctness says that decrypt on input the secret key and the ciphertext generated using the encrypt algorithm outputs F of M. The simulation security says that whether we generate the ciphertext using the honest encryption algorithm or we generate the ciphertext using the simulation encryption algorithm, it is indistinguishable. In key policy functional encryption, the role of F and M are swapped, that is, encrypt takes as input M and keygen takes as input F. In dynamic bounded collusion model, the Q is chosen per ciphertext by the encryptor, and the setup and keygen algorithm are independent of this collusion bound Q, and the ciphertext size grows linearly with Q. So the encrypt and decrypt algorithm takes one additional parameter, that is collusion bound, as the input. Now let us see what the simulation security for KP-ABE is. In adaptive simulation security, there are two worlds, real and ideal world. In real world, the ciphertext is generated using the honest encryption algorithm, that is encrypt. In ideal world, the ciphertext is generated using a simulator, that is SimEnc algorithm. And both these worlds should be indistinguishable. Note that in adaptive simulation security, the adversary can have pre and post challenge key queries. In non-adaptive simulation security, the adversary cannot have post challenge key queries, and here also the real and ideal world should be indistinguishable. In selective simulation security, the adversary outputs the function at the start of the game. So now let us look into the related work. Basically, we would be looking towards the work which is in dynamic bounded collusion model. Agrawal et al. Constructed functional encryption for Turing machine, which is non-adaptive simulation secure, which is from the assumption of that is sub-exponential hardness of LWE with sub-exponential approximation factor. They also constructed FE for Turing machine. FE for adaptively simulation secure FE, but at the cost of supporting lower class, that is NL. Goel et al. Constructed ABE for Turing machine, which is adaptively indistinguishable secure from IBE, but it is secure in random oracle model. Note that in these work, the encryption time of Turing machine depends on the running time of the computation. In our work, we construct FE for Turing machine, which is adaptively simulation secure from LOT, ABE for NC1 and PIR. Since LOT, ABE for NC1 and PIR can be based on different other assumptions, we get FE for Turing machine from polynomial hardness of LWE with quasi-polynomial approximation factor, DDH and DBDH, and QR and DBDH. We also obtain FE for Turing machine, which is adaptively indistinguishable secure from IBE and LOT. We also construct a simpler version, that is, we construct adaptively simulation secure KP-ABE for a circuit, which is of unbounded size and depth from IBE and LOT, and this may be of independent interest. So now let us see the roadmap of our construction. We combine in a careful non-black box manner gate-by-gate garbled circuit and bounded CPFE to get unbounded CPFE. This unbounded CPFE is adaptively simulation secure. Then using the ideas of Agrawal et al., we get TMFE with fixed machine size, and then we get adaptively simulation secure TMFE. In the second result, we get FE for laconic oblivious transfer from IBE, ABE, and PIR. This FE for laconic oblivious transfer is non-adaptive simulation secure. Using FE for laconic OT, we construct CPFE for RAM. Using CPFE for RAM, we construct TMFE with fixed input length. And then combining the bounded CPFE and TMFE with fixed input length, which is non-adaptive simulation secure, we get adaptively simulation secure TMFE with fixed input length. In this talk, I would be presenting the second result. So let us begin by recapping the ideas of construction of TMFE by Agrawal et al. To construct FE for Turing machine, Agrawal et al. Used a compiler which was developed by Agrawal et al., where to construct FE for Turing machine, we divide it into two categories, one where the machine size is unbounded and one where the machine size is bounded. So to construct FE for Turing machine where the machine size is bounded, they constructed non-adaptive simulation secure CPFE for unbounded circuit, and one where the machine size is unbounded, they constructed FE for Turing machine in that case by constructing adaptively simulation secure KP-ABE for unbounded circuit. This adaptively simulation secure KP-ABE was constructed by upgrading the succinct single key KP-ABE of Goldwasser et al. From sub-exponential LWE. Our goal is to construct the adaptively simulation secure functional encryption without relying on succinct KP-ABE. So before diving in, let us see what the RAM model of computation is. There is a program P which takes as input X and T, and there is a database M. The RAM program takes as input the rate location I, interacts with the database, and outputs D of I. The oblivious RAM is a compiler which takes as input the rate location I, converts this read command into some read and write command, and interacts with the database, and outputs D of I. The security says that this ORAM hides the access location I. So the motivation for RAM model of computation is that we have to construct FE for Turing machine for the case where the machine size is unbounded. So we can think of M as a large database, X as a short input, and T as a bounded running time. So this naturally suggests the idea of RAM model of computation. So when we run M on X, we will have bounded number of lookups in the transition table and the bounded number of steps, because here T is bounded no matter what the size of the database is. So we have a program P which has a RAM access to a database M, and this program P executes M of X. We introduce a new primitive called CPFE for read-only RAM, where the encryptor encrypts the program P. Keygen provides the key for the database M. The decryptor executes this program P on X to give M of X. So to construct CPFE for read-only RAM, we build upon the ideas that were developed in the context of RAM construction of Lu et al. Here there is a garbled RAM program which consists of T garbled copies of augmented step circuit. Here each copy I takes as input current CPU state, last read bit, and outputs updated state and the next read location. The copies are garbled in such a manner that the labels of the output of copy I matches with the labels of input of copy I plus 1. These copies interact with the memory to incorporate data into the computation, and previous works used IBE and oblivious RAM for this incorporation of data. IBE chooses correct label for the garbled circuit, and oblivious RAM is used to hide the position rate. But the problem with oblivious RAM is that we have a program and a server, and they need to agree on a secret key. In our setting, it means that the program key corresponds to the encryptor and the server corresponds to the key generator. So it means that the encryptor and key generator should agree on a secret key. But this is not possible because we are in a public key setting. So to overcome this problem, we introduced functional encryption for laconic oblivious transfer. In functional encryption for LOT, the encryptor has two messages, mu0 and mu1, and a database location I. The keygen has input the database. The decryptor allows to recover mu of di, but mu of 1 minus di and I are hidden. So to construct FE for laconic OT, we need to support table lookup functionality. We can replace FHE of FHE, which was used in the construction of succinct KP-ABE of Goldwasser et al., by much weaker PIR. And we can also replace ABE for circuit by much weaker ABE for NC1. So if we have adaptively indistinguishable secure IBE, selectively indistinguishable secure ABE for NC1, selectively secure garbled circuit, and a private PIR, then we can construct one NA simulation secure FE for laconic OT. So we constructed FE for laconic OT using IBE, ABE, and PIR. Using this FE for laconic OT, we constructed CPFE for RAM. And using CPFE for RAM, we constructed TMFE with fixed input length. Note that all these constructions are non-adaptive simulation secure. And to make it adaptively simulation secure, we combine this bounded CPFE, which is adaptively simulation secure, and non-adaptive TMFE with fixed input length to get TMFE with fixed input length using the ideas of Agrawal et al. Thank you.
Great. So we have time for a couple questions. Mohammed?
So for your definition for FE for laconic OT, where the encryption algorithm takes as input a pair of messages and an index I, does the resulting ciphertext hide the index I? Because for laconic OT, the second message of the OT protocol doesn't hide the index I that is kept by the sender. Yeah, so I'm wondering, the ciphertext that is generated by the encryptor, does it hide the location I? Because in general, under laconic OT, the constructions that we have, the index I is not kept hidden by the second round OT protocol message.
Yeah, were you able to hear the question?
Yeah, I'm able to hear the question.
Sorry? So maybe in the interest of time, we can take this offline and move on to the third speaker.
Yeah, okay.
So
Thank you.
it does hide the index. If I may jump in.
Cool. So let's thank the speaker again.
Thank you.
Okay. All right, so our final talk for this session will be on ABE for circuits with constant size secret keys and adaptive security. This is work by Hanjun Lee, Weijia Lin, and Ji Luo, and Hanjun will be giving the talk.
It is a joint work with Rachel and G. So the attribute-based encryption, ABE for short, has the following syntax, where an administrator first runs the setup to produce the master keys and send the master public key to an encryptor who encrypts messages MI, each with an attribute XI associated with it. For someone, if someone later wants to have partial access to the messages, the administrator will use the master secret key to run keygen, produce a secret key associated with some policy FJ. And the correctness requires that if a secret key for FJ, a secret key FJ can decrypt a ciphertext for attribute XI if FJ of XI equals 0. The scheme is secure against colluding adversaries who hold multiple secret keys with different policies. If each of the keys separately cannot decrypt the ciphertext with attribute X star, then the message M star should remain hidden. In the formal security game, the adversary is allowed to choose the challenge attribute X star, as well as the policies of themselves. And adaptive adversary chooses X star and FJ after seeing the master public key. A weaker selective security chooses X star before seeing the master public key. So the other CP variant is similar, but the role of the policy and the attributes are flipped, and correctness and securities are defined analogously. So an important aspect of the efficiency of ABE is the size of the ciphertext and secret key. We measure those against the length of the attribute X and the description of the policy F. So a natural requirement is to have ciphertext and secret keys polynomial in the size of X and F respectively. A stronger requirement is to have linear size ciphertext and secret keys in X and F, which is also called compactness. And is compactness the best efficiency we can hope for? It seems so because the decryption algorithm needs access to X and F, which needs to be transmitted through the ciphertext and secret key. But we realize that X and F are not hidden in this scheme. So we can transmit those in the clear, and that is in the modified syntax, the decryption algorithm takes X and F in the clear in addition to the secret key and the ciphertext. Hence, we can have ciphertext and secret keys of size smaller than X and F. So if a secret key or ciphertext has size sublinear in X or F, we say it's succinct. And if an ABE scheme has both, then we say it's doubly succinct. Finally, the dream efficiency is to have constant size ciphertext and secret keys, independent of X or F. And among known constructions of ABEs are mainly two approaches, one based on pairing and one based on lattices. So, and they each have advantages and some limitations. So pairing-based constructions achieve ABE for low depth policies only. And the constructions achieve different trade-offs between the size of the ciphertext and the secret key, but their product happens to always be at least the size of F times X. So pairing-based constructions can achieve constant size secret key or ciphertext, although not both at the same time. And they can achieve the stronger adaptive security. On the other hand, the lattice-based constructions achieve ABE with policies in P, and the state-of-art schemes can achieve secret key and ciphertext with size poly in D and X times poly in D, where D is the depth of F. However, those constructions have the limitation that they only achieve selective security. And it's a fascinating technical barrier to achieve adaptive security without relying on complexity leverage. Now I'll plot the known efficiency of the known constructions in this graph. The state-of-art lattice schemes have size poly in D and X times poly in D. The pairing-based constructions achieve different trade-offs, but their product is at least X times F. And given this current state of affair, we ask if we can move closer to the dream efficiency, which lies in the left bottom corner. And as mentioned before, the two approaches have their advantages and limitations. So we also ask if we can combine pairing and lattice technique to help overcome those limitations. And a recent beautiful work of AY and AWY is such an example, combining lattice and pairing to construct the KP-ABE for NC1. And they improve the size efficiency to achieve succinct secret keys with size linear in X instead of F. And the construction inherits the selective security from the lattice world. And now I will show our result and where they land in the efficiency plot. So first, we're assuming LWE, and in the generic pairing group model, we construct a KP-ABE scheme for P. The first scheme, KP-ABE for P, that have constant size secret keys. And previous such schemes have secret key size at least polynomial in D. We also construct the KP-ABE for NC1, also having constant size secret keys. And at the same time, the ciphertext encoding a policy F also has size independent of F. Hence, it's a doubly succinct scheme. And if we replace the LWE assumption with the adaptive LWE introduced in QWW, then both schemes achieve adaptive security. Okay. Our constructions at a high level starts from the lattice-based secure function evaluation protocol introduced in QWW, which is similar to but weaker than one-key secure ABE. And we use the pairing to lift it into a multi-key secure ABE scheme. So note that the known KP-ABE scheme for P, they use the celebrated lattice trapdoor technique, but this also creates a bottleneck because the trapdoors usually live in the secret key have size polynomial in D. So the keys are large, and we only know how to show selective security when the trapdoors are involved. This SFE protocol avoids lattice trapdoors, and it's also it avoids the trapdoors in its construction and also in the security proof. And it's adaptively secure from the adaptive LWE assumption. This gives us a new way towards adaptively secure ABE. And the difficulty we will face when combining lattices and pairing comes from the fact that in the lattice world, we'll generate large noises from homomorphic evaluation and the use of noise flooding. While in the pairing world, we hide information in the exponent of the pairing groups, which can only tolerate small noises. And next, I will give a quick overview of the SFE protocol, which involves a sender and a receiver each holding a attribute X, a message M, and a policy F. The goal is for the receiver to learn the message M if and only if f of X equals 0. And the protocol uses two homomorphic evaluation procedure first introduced in the celebrated work of DGG plus 14. So the receiver first runs eval PP over the public matrices to compute the digest AF. And then the sender encodes its attribute in the following format, where S is the LWE secret, G is a gadget matrix with a public trapdoor G inverse. And using the second evaluation procedure on the attribute encodings, the receiver can get S times AF plus f of X times G. When f of X equals 0, this term becomes S times AF, which multiplied with G inverse of U, we get this term in the blue box. And the sender uses computer message encoding using exactly this blue box term to hide the message. So the receiver can subtract those two to recover the message. And an attempt to cast SFE to a KP-ABE is to set the master public key as to be the public parameters, and also the ciphertext to be CTX and CTM. But the issue is this CTM term is dependent on the policy F, which is unknown to the ABE encryption algorithm. And it's also not clear what the secret key should be. We use a pairing-based IPFE scheme, which allows us to break an inner product between U and V into an IPFE ciphertext of U and the secret key of V. The security hides U and reveals V and the inner product in the exponent. So now we can break the problematic term CTM into an IPFE ciphertext of S and M, and the IPFE secret key of the rest of the term, which may depend on F. And note that the decryption result of this IPFE lives in the exponent of the target parent group instead of in the clear. And now to verify correctness, we follow the previous procedure. First, we run eval CT to get the blue box term, and then subtract it from the CTM term. But the difference is that now the CTM term and hence the recovered message live in the exponent of the target group. And to recover it in the clear, we need to be able to compute discrete logarithm. And whenever we are dealing with the lattices, we need to be careful about the noises, because the attribute encoding each have some noise. This will generate a homomorphic evaluation noise in the blue box term called EF. And what we recover actually is M plus EF in the exponent. And this first correctness problem is that this EF noise is huge. And it's exponential in D, and so we cannot do discrete log efficiently. Another efficiency problem is that the modulus Q, because of the large noise, is also huge, giving us a large ciphertext size of a polynomial in D. And our solution is to apply rounding to the blue box term. We round it down to a much smaller modulus P that's independent of D. And this rounded term roughly equals S times AF G inverse U, rounded down to P, plus some small error terms. And now we also apply rounding to the secret key. And what we get is M minus the small error terms in the exponent instead. Since the error terms have small magnitude, we can now compute discrete logarithm efficiently. And this gives us a correct ABE scheme. And note that the rounded modulus P is also small, hence we have constant size secret keys. Other challenges involves first proof one key security. The original SFE scheme relies on noise flooding, particularly in the term CTM, which we cannot afford to do because CTM lives in the target parent group, the exponent of the group. What we do is to just remove the flooding noise, and we are able to still show that the term is entropic, and although not pseudo-random, but this is already enough for security in GGM. And to obtain multi-key security, we borrow ideas from AY and AWY, which also relies on GGM. And further detail you can find in our paper, which is on ePrint. Thank you.
So we have time for maybe one question. So. Yeah.
So maybe I missed it, but can you say where the quadratic dependence comes from in your second theorem?
Oh, where the X star?
That's right.
Oh, X star. Oh, yeah. I didn't mention the KP-ABE construction at all. It's because in the CP construction, we in the IPFE well, in the CP construction, we're encoding the, what can I say? Simply.
We can take it offline. So,
Yeah.
sorry,
I
yeah.
don't remember.
Okay, any other questions? I have one really quick one. So do you see any hope of replacing the GGM with a concrete assumption? So I think AWY was able to show it from this new knowledge-based assumption over pairing groups. Do you see something similar here?
We tried for a while to formulate some knowledge assumptions, but not very successful.
Okay. Great. So let's thank the speaker and all of the other speakers in the session. And now we have a coffee break.